In 2023, China generated 9.5 million gigawatt-hours of electricity. The country is executing a rapid shift away from imported fossil fuels, and sustaining its economy requires producing power on a scale unmatched anywhere else on the planet. This map illustrates the country's core geographical mismatch. The overwhelming majority of the population and energy demand are concentrated on the eastern seaboard. The water resources required to generate that power are located thousands of kilometers away, high in the 5,000 to 6,000 meter elevations of the west. Bridging that massive geographical gap has driven an explosion in infrastructure. Over the past 2 decades, China's hydropower generation has surged from 222,000 gigawatt-hours to a staggering 1.3 million gigawatt-hours in 2023. The physics driving this output relies on a metric called head difference. In hydroelectric generation, the vertical drop in altitude is the key parameter. The further the water falls, the more kinetic energy it transfers to the turbines, allowing for massive electrical power generation. To exploit this paradox, civil engineers must place the largest, most rigid concrete structures in the world deep into volatile, narrow mountain gorges. The western river systems, particularly along the Jinsha and Yalong rivers, feature some of the most severe altitude drops on Earth. The environment is incredibly hostile to heavy construction. This 3D wireframe shows what happens when you block one of those steep gorges to create an artificial high-altitude reservoir. You immediately generate exponential hydrostatic pressure, the raw physical weight of billions of liters of water pressing constantly against the barrier. The core structural vulnerability is forcing thousands of tons of rigid concrete to endure that immense localized pressure without catastrophic cracking. Solving this physical constraint required moving away from conventional designs. Engineers had to pioneer complex double curvature geometries and deploy artificial intelligence to remove human error from the construction process. China's hydroelectric sector relies on a rigorous application of civil engineering to force concrete and bedrock to their physical limits. The Jinping 1 Dam on the Yalong River perfectly illustrates this geometry. Rising 305 meters, it is the tallest arch dam in the world. The structure sits in a narrow valley with a highly weathered foundation. The underlying bedrock consists primarily of fractured marble and sandslate. This fragile bedrock profile makes a traditional gravity dam physically impossible. A gravity dam relies entirely on its own massive weight to hold back the water. This schematic demonstrates the mechanical solution. A precise arch design catches hydrostatic pressure, redirecting it horizontally into stronger valley abutments. Because the left riverbank was too weathered, engineers poured a massive concrete cushion, a buffer layer distributing force vectors safely against the weak rock. They reinforced the lower foundation with high-strength concrete to manage compression, and wove complex steel reinforcement into the upper sections to ensure seismic stability. Jinping 1 proves that intelligent structural geometry can override inherent geological weaknesses, allowing engineers to safely harness extreme hydrostatic head differentials. Moving up the capacity scale, the Baihetan Dam on the Jinsha River generates an immense 16,000 megawatts of installed capacity. For context, only China's Three Gorges Dam has a higher output, possessing an unmatched 22,500 megawatt capacity and spanning 2.3 kilometers across the Yangtze River. Baihetan is unique because of its structural architecture. It's the world's largest arch dam to utilize a double curvature design, curving both horizontally and vertically to adapt to the gorge's deep constraints. Building a structure of this complexity introduces severe logistical friction. Executing a massive double curvature pour within a 4-year timeline creates high risks of thermal cracking. If the concrete sets at the wrong temperature, the entire structure is compromised. To solve this, AI systems completely managed the logistics. Algorithms autonomously handled cement mixing, routed delivery vehicles, and strictly regulated pouring temperatures without human intervention. The payoff was the interior real estate. Baihetan successfully housed 16 1-gigawatt hydroturbine generators, the first time turbines of that scale were successfully deployed anywhere. As hydroelectric facilities scale to multi-gigawatt outputs, their structural integrity relies exactly as much on autonomous algorithmic logistics as it does on raw materials. The absolute frontier of topographical engineering lies further west, at the planned Medog hydropower station on the Yarlung Songpo River in Tibet. Upon completion, the facility is expected to generate nearly 3 times the capacity of the Three Gorges Dam. Rather than relying on a single massive concrete wall, the Medog project will utilize a cascade architecture, stepping the water down through a series of 5 separate dams. This elevation cross-section displays the topographical feature making that output possible, an extreme 2,000-meter drop compressed over just a 50-kilometer stretch of river. However, damming steep western rivers exposes a critical technical flaw, the severe disruption of natural sediment morphology. Fast-flowing natural rivers constantly erode the surrounding landscape, transporting massive volumes of silt, sand, and rock aggressively downstream. This reservoir cross-section shows the mechanics of siltation. When flow hits the dam, it loses kinetic energy, causing suspended sediment to drop and settle at the bottom. This buildup alters carefully calculated hydrostatic pressures, eventually rising to physically choke off the deep water turbine intakes. Harnessing extreme elevation drops forces engineers into a perpetual, unwinnable battle against the river's natural geological cycles. Moving outside the mechanical structure of the dam, the operational demands of the electrical grid create an entirely different set of problems. To satisfy an energy-hungry economy, turbine operations cannot mirror natural weather patterns. They must run year-round in a continuous, uninterrupted manner. To guarantee steady output, operators must retain as much water as possible behind the dam, ensuring maximum head pressure at all times. This graph plots an undammed river system. It features deep seasonal variances, periods of low-flow droughts, followed by massive high-flow flood events. But continuous turbine operation writes over that natural cycle, creating a synthetic flow pattern that flattens out both the peaks and the valleys. The immediate environmental consequence is downstream starvation. Floodplains are permanently denied the high-water flood events required to naturally irrigate agricultural lands. Achieving perfect mechanical efficiency inside the turbine inherently demands the destruction of the natural hydrological cycle outside of it. This map traces the upper reaches of the Mekong River, projecting that localized flow regulation onto an international scale. 11 facilities, including the massive Shawan Dam, allow operators to dictate water levels flowing out of China into Thailand, Laos, Vietnam, and Cambodia. During regional droughts, Chinese reservoirs retain water to protect power generation, severely dropping the water and fish levels available downstream. That same mechanical vulnerability is now looming over India and Bangladesh, who sit entirely downstream of the planned Medog Cascade. These megadams function as highly specialized industrial assets, manipulating weak geologies and AI logistics to harness topographical power. But they act as machines that transfer the continent's energy inward while pushing the ecological and political costs downstream.